Hello, my name is Max Daughtry, and today I'm going to be presenting my poster on the resistivity size effect of ruthenium nanowires. So to start off with, Moore's law has been slowing down over the past decade, and a main contributor to this is the resistivity size effect. So basically, as metals approach nanoscale dimensions, their resistivity starts to grow exponentially. This is a problem for the world of electronics because basically the power demand starts to get so high we can't reasonably make the interconnects any smaller. Thus, we can't fit more chips onto or more transistors onto chips. So this effect for copper is very great. The copper's resistivity starts to grow very quickly as it approaches nanoscale dimensions, especially compared to other metals such as ruthenium. So there's actually a point where copper's resistivity crosses ruthenium's, and the resistivity of copper becomes greater than that of ruthenium. So it's pretty widely believed at this point that ruthenium is a suitable replacement for copper in the coming years. So our group's main goal is to reliably develop and test resilient ruthenium nanowires. And on top of that, we're also looking for ballistic transport, which I'll talk about later. Basically, the process of creating these ruthenium nanowires starts with a deposition of ruthenium onto sapphire substrate by DC magnetron sputtering. So we then test the quality of these depositions using characterization techniques like XPS, XR, and STM. So X-ray, photoelectron spectroscopy, X-ray reflectivity, and STM, or scanning tunneling microscopy. And alongside of this, we also send off some of the wafers or some of the depositions to a third-party contractor, Plasmonics Inc., where they do e-beam lithography to create our nanowires for us. And so once we get these nanowire devices back, we can put them onto a probe where we can send constant current through them and measure the voltage drop across a selected length of the ruthenium nanowire. And so this here is actually a schematic of what our ruthenium nanowires look like. So we basically apply a constant current through this section, and then these two probes that are coming in, which are also ruthenium wires, measure the voltage drop across this section of the wire here. And so the reason that we use this 4-probe technique is that if we were to use a classic 2-probe technique, we would be measuring the resistance of the wire, but we would also be measuring the resistance of the probe, the wires connecting the probe to the ohm meter, and we'd just be getting resistance that we don't actually want to measure. So we use this 4-probe technique instead. And so once we measure this voltage and when we have this constant current, we can then calculate the resistance of this length of wire in between. And this is a schematic of kind of the theoretical 4-probe technique. So yeah, we can. So when we take these measurements, we take one at in liquid nitrogen and one in liquid helium, as well as a room temperature measurement. And when we do this, we can calculate the resistivity ratio of higher temperature to lower temperature, which of course higher and lower are very relative. When we do this resistivity ratio, though, it allows us to detect ballistic transport, basically. And so ballistic transport is where the mean free path of the electron becomes larger than the length of the wire itself. And so the mean free path of an electron is basically how far it can travel without a collision. So if the mean free path is longer than the wire itself, then it could, in theory, travel through the entire distance of the wire, or that section of the wire, without making a single collision, effectively having a resistance of 0. Um, so what we'd expect with our resistivity ratio, if we're taking the the ratio of higher temperature resistivity to lower temperature resistivity, is a large increase in that ratio, because the mean free path is dependent on temperature. So with a lower temperature, we have a longer mean free path, which means at lower temperatures, we're more likely to observe ballistic transport. So our data does suggest a ballistic transport phenomena happening. So with this point here, which is clearly far above, clearly a higher ratio than the rest of the data points, it does suggest ballistic transport, but we definitely need to do a few more measurements and a few more tests before we can confirm this. Another thing to point out is that this resistivity ratio is pointed or plotted versus the length of the wire themselves. So our longest wire here is 2,000 nanometers, and it goes down to 60 nanometers. And it seems we observed the ballistic transport on a wire of 65 nanometers long, and we would expect that that we would observe ballistic transport on the lower side, because essentially we're getting closer to the point where the wire is shorter than the mean free path. So to go into the results of all this this whole process, it seems that our deposition process is very reliable, and we consistently get excellent depositions of ruthenium. And we found that annealing the ruthenium wafers results in a much more consistent single crystalline structure. The annealing process effectively reduces or eliminates any grain boundaries we're getting between the crystalline structures, which greatly reduces resistivity. It seems that the e-beam lithography process is where we're getting most of our contamination and defects in the ruthenium. So it seems that the e-beam lithography leaves a residue, or splotches of residue, uh, um, just due to the inherent process of e-beam lithography, and maybe adds some defects to the ruthenium itself. Our goal is to use an annealing process to remove these defects and find a way to remove any of this contamination that we're getting. Also, the team has found in the past, before I had joined, that leaving the ruthenium nanowires at 60-degree angles from each other results in much stronger wires. And the reason for this is that the underlying sapphire substrate support structures, or the crystalline structure of the sapphire, is hexagonal. So at angles of 60 degrees, the ruthenium wires are laying more directly on that support structure of the ruthenium, which means that it's more resilient to annealing, which annealing will be an important process in removing any defects that were previously introduced by the e-beam lithography process. So currently it seems that the two most common failure modes are contamination and broken wires. And we actually have, we did a scanning electron microscope image of some of our wires recently. And this is actually one that had broken. So you can see right there, it's a little hard to see, but there's actually a break in the wire here, which effectively means that this wire is useless to us. So that's what I mean by failure modes. Not necessarily not necessarily having defects or anything like that, but wires that we're just not able to measure. So contamination can also lead to that. If we have a big splotch of something right here, which did happen, it can definitely mess with our measurements and not get us anything useful. So the broken wires can most likely be attributed to just general handling, exposure to environment, possible electrostatic discharge. But we try to do everything we can to reduce those factors. Um, and the contamination seems to mostly come from the e-beam lithography process, which we're working on getting that sorted out. So altogether, um, our resistivity data seems like it's modeled very well by this Fuchs-Sonheimer model um, for the resistivity of the single crystalline sheets. So not necessarily the wires, but that's probably mostly due to the defects that we've added to it through the lithography process. Um, Again, our data does suggest ballistic transport, although the resistivities are still very high. We do, however, know that high resistivity can mostly be credited to the lithography process. So naturally, our next steps are to try to get those wires back to their pristine state and eliminate any defects and contamination that was introduced with the lithography process. This will probably be done using an annealing process and maybe some other things along with the annealing process. Um, so yeah, thank you very much for your time. I would also like to thank the Society of Physics students and the National Science Foundation for granting me the opportunity and funding to participate in this PhysCon 2022 event. And I would also like to thank the U.S. Department of Defense for the funding that has made this research possible. So thank you again for your time and have a great day. Thank you.